All right, so for the next talk, we have hot cold chain inlining for GHC, presented by Celeste Hollenbeck. And so please go ahead.
Okay. Hi, everyone. I am Celeste Hollenbeck, a soon-to-be graduated PhD student at the University of Edinburgh, and you presumably are here to see me present the last work in my thesis, hot call chain inline for the Glasgow Haskell Compiler. Okay, so let's start at the beginning. What is inlining? It's very simple. You just replace the call of a function by an instance of its body. So we're in our code and we're going to call out to a function, and maybe during compilation we're going to take a copy of that function's body and we're going to place it directly in the line of code so that we can avoid that extra function jump, basically. It sounds simple, but don't be deceived. Inlining optimization is actually NP hard. If you do it right, we can expose opportunities for further optimizations, and we can get, as a result, smaller and faster code. But if we do it wrong, we can get bigger and slower code. We can have cache misses. We can have register spilling. So why is it that inlining is important in Haskell? And if we look at imperative languages, about 10 to 18% of their performance improvement comes from inlining, whereas in Haskell, about 40% of performance improvement comes from inlining. And I want you to take note that these numbers came from some work that was done in 1995. But the inliner in GHC has not significantly changed since then. So if inlining is such an important optimization in Haskell, why is it that GHC's inliner has not significantly changed in about 30 years? Part of this, I think, is that it's very complicated. But on a high level, what the inliner is doing is it's going to calculate the size of the thing that it's considering inlining, the expression, and then it's going to calculate some benefit of inlining it. These are both numerical values. It's going to take that benefit, it's going to subtract it from that size, and if the numerical value that's left over is less than some threshold that's set in GHC, then it's going to inline that thing. And if it's not, then it's not going to inline that thing. And on a high level, this is pretty much what that heuristic looks like at the point of that decision. I'm not going to bother explaining this because, as aforementioned, it's complicated. And to further explain that, if you do a string search for the word core unfold in GHC, where core unfold is basically just another name for a potential inlining candidate, if we do that search, then we get about 30 files that come up, which basically means that what goes into making that decision is basically scattered throughout the compiler. So something that an average Haskell programmer can do if they want to try and influence inlining in their own programs is they can put in an inlining pragma. And an inlining pragma is a compiler directive, and you put the inlining pragma near the definition of the thing that you want GHC to try and inline if it's not inlining it already. And an interesting observation here is that in stackage is like this big collection of Haskell packages where a package is like a bundle of code that has maybe tests and benchmarks and preferred run flags and whatnot. About 20% of the packages that are in stackage have these inlining pragmas. And when we saw that, we thought maybe this is some sort of an indication that Haskell programmers are maybe a little bit dissatisfied with the inlining decisions that GHC makes. And maybe they have some specific suggestions of where it can inline a little bit more aggressively. So the question that we want to answer is, how do we improve inlining in GHC? And it seemed like a sane place to start looking is in the simplifier. The simplifier resides in the middle of the compiler, and it happens after parsing, renaming, type checking, desugaring. It takes in an intermediate representation called core IR. And then it does kind of like a lot of optimizations over this, like including rewrite rules, strictness analysis, let floating, specializing of overloaded functions, and inlining. And it outputs core IR again. So the core IR can go through the simplifier multiple times. That's part of why it makes this problem so hard, because inlining optimizations, they kind of provide more opportunities for more optimizations, including more inlining optimizations. So we approached the simplifier, and one of the first things that we tried was a genetic algorithm. My advisor actually did some interesting work with Java that had some promise to it with a genetic algorithm. And so when I tried it in Haskell, what we do, we take in features. A lot of them were features that were considered with GHC's original inliner and maybe some more additional features. It goes into this genetic algorithm, and the genetic algorithm produces these candidate populations of new inliners, and it kind of produces them in this probabilistic manner with like mutations and stuff. And then you take these inliners and you run your benchmarks on them, and you take the best ones and you breed them together, and they turn into your next generation, right? And you kind of rinse and repeat this for a while. And what happened is that one generation took an average of about 2.3 days. And there are reasons for that. Like GHC compiles kind of slowly. It's a known issue, and you can parallelize some of that with the build. But we can't really parallelize the execution time, because if we're measuring actual time, then we can't have any other processes running on that computer because it's going to affect the time. And then additionally, we had some issues with Cabal that added some extra time. So usually you need about 100 of these generations if you want to start seeing some interesting results with the genetic algorithm. And if we calculate maybe a worst case situation, that would be maybe 230 days to run this thing and get some interesting results. And that was a little bit prohibitive. So that kind of went on ice, because we thought, what if we combine this with maybe another approach so that it's not starting from scratch? Or maybe if that other approach works, we'll go with that other approach or something. And the other approach that we tried was neural networks. So the training data that we got for these neural networks came from some previous work that we had done, where we were tweaking something called magic numbers in the inliner. And magic numbers, they're really just like hand-coded numbers in the inliner. They're very arbitrary. Things like, okay, this is the number of discount that we'll give for a certain type of argument or whatever. And they're just littered throughout this inliner. So we played this with those magic numbers, and we found out for a number of packages what their preferred magic numbers were. And so with this approach, we have the machinery to produce like a lot of labeled training data for good and bad inlining decisions. And we take that and we train our neural networks with it, and we get these new candidate inliners. And what happened is these neural networks, we trained them to a very high accuracy, like 99% and above, and they still did not help performance when we plugged them in. And it's not like they were doing nothing, because if you just do like a random inlining decision, then it usually, like often it doesn't work at all and it just chokes. So they were doing something, but it was pretty much on par with default GHC. And there are reasons why I think this happened. I go into them in my thesis, which is not published yet, but I don't have time to go into it now. So after trying to make some progress on that, we tried a different approach, which maybe might have been lower hanging fruit, we thought. And that was like, what if we, instead of going through the simplifier, because the simplifier, we've already desugared everything down to this core IR, right? And so we're making like between 1 and 1.5 million inlining decisions for each package just on a regular basis, right? What if we look at it from a higher level in the source code? So if we look at it in the source code, maybe we can predict where we can put inlining pragmas, right? Because then we're looking at dozens or hundreds of functions versus millions of inlining decisions. So what we did is we used the abstract syntax trees, and we pulled the functions out of those in graph form. And then the labels on those were whether or not it should have a pragma attached to it. And how we actually got those labels came from a few different ideas. Some of them came from allegedly good examples in the wild, and then others were ideas that we concocted on our own. And in retrospect, these approaches, they were misguided for reasons which I can't go into now. But at the time, I promise you, they seemed sane. So we used this training data, trained our neural networks, and again, we got them up to really high accuracy, like 94% and above for packages, and they still didn't significantly help performance. Okay, so at this point, it's like we tried a lot of machine learning, right? And it did not work. Okay, let's try one more thing. we looked really closely at the source code, specifically at instances where inlining pragmas gave us a really big performance improvement, right? Because there's got to be some information there that we're just not seeing. And so to go further, I need to explain to you the difference between the different types of inlining pragmas. We've got two of them for GHC. One is inlineable, and one is inline. The inlineable pragma is going to give like a big extra discount to the thing that you attach it to, but GHC can still decide whether or not it wants to inline it. The inline pragma, GHC is going to inline that thing unless it's going to break something. And it's notable that for both of these pragmas, they will allow functions to specialize across modules. So if you have like a function that's overloaded and it takes in different types of parameters, that'll get implemented usually as like a dictionary lookup. Whereas if you attach this pragma to it, that will ensure that the compiler has enough information at compile time where if it knows that a specific type is going to be used, then it can go ahead and inline that type and we can get the nice optimizations. Okay, so what we saw in the code, what we found, is that where the pragmas made a really big improvement, often, they occurred in like these chains or these graphs. And I'll give you kind of an abstracted example of one. Here at the top, we have a wrapper. The wrapper exists to pass arguments to the worker. The worker goes and does the actual work. And like maybe it has some sort of like a custom operator, and maybe that custom operator will call down to something that is expensive. So some concrete examples of what an expensive thing are that I've actually seen. One is convolution. So that's like mathematically combining two functions, super high level explanation. Another example was something called karatsuba, which is a fast matrix multiply. Okay, so we have these functions that are in these chains, and they go down to something expensive, and they all have inlining pragmas attached to them. Cool. Okay, so what if we inline the whole call graph per hotspot? And a hotspot here is just, you have a function or a bit of code that takes a really long time to execute, so it's really computationally expensive. If we want to do that, we need some sort of control flow. So the thing is, in functional languages, call graphs are really expensive. Like if you want some sort of like a context-sensitive polyvariant analysis, that's going to be exponential time complete. And if you're not so choosy, and maybe it's okay if it's context-insensitive, that's going to be cubic. And neither things are super, super easy to implement in practice. So we started with using the abstract syntax tree to over-approximate control flow. Let's try it. Why not? The abstract syntax tree it's just like a tree representation of the program's syntax. And there's a nice flag that you can pass to GHC that's going to dump out that parsed syntax tree. And here's just kind of an example. This is a function in Haskell. It's not even 7 lines long. And if we ask for the AST on that, we get about 279 lines of AST. And this is a very, very simplified graph form of them. But up at the top there, you have this thing called funbind. That's the root that indicates that it's a function. So the point here is that the AST will often reveal when functions are associated with other functions, because other funbinds will be attached in that AST. So we locate the hotspots via profiling, and then we look at their ASTs, and we find all of the funbinds, the names of functions that are associated with them. And of course, other funbinds in this AST may have its own AST, and then you need to find the funbinds that are associated with those. And if you just do like a fairly simple fixed point thing to kind of collect all of them, that ends up being about quadratic. Okay, so how do we get the hotspots? Yes, so GHC has built-in profiling functionality. You have some target that you can run. You're going to build it with some profiling flags. You're going to run it with some profiling flags, and you're going to get this nice .prof file. So the profiling report, the .prof file, has kind of this table at the bottom that lists cost centers. And a cost center is something that has significant runtime or number of allocations. So by default, GHC will qualify something as significant if it has 1% or greater of runtime, or 1% or greater of the total percent of allocations. And for the results that I'm going to be showing you, we just go ahead and use those default values, but we do change them a bit in the paper, and you can just arbitrarily change them and see what happens. The experiments. We profiled packages from Stackage. We collected our packages from Stackage. We wanted them all to build successfully, of course. We wanted them to have tests that ran for a reasonable amount of time, so maybe over half a second. And we wanted them to compile and run all of the tests in less than 20 minutes. And we preferred that they had developer inlining pragmas because we were going to do some fun things with those as well. OK, so we collect all the hot call chains in those packages. And then for the hot call chains, we attach, for each experiment, all inline on all of the call chains, or all inlineable. Actually, we collect both, of course, so that we can observe what happens. And the things that we're observing are, again, runtime, actual runtime. And the baseline is default GHC, default cabal commands, no inlining pragmas. So we're going to take the developer pragmas out so that we can just see what GHC would have done on its own. So the first thing that we tried is called the naive approach, and that's where we just look at the profiling report and we find all of the significant cost centers, and we're gonna attach an inlining pragma to each of those call centers. We're not gonna bother with the chains that they're associated with. When we do that, we get about a 2% mean speed up. So notably, we have like 2 packages here that we have a really significant performance improvement. Cool, but the rest of them are 1% or less. So for the remainder of the experiments involving the call chains, we needed a little bit more machinery. But basically what it does is we take all of the function names and bundle them together. And then we have a binarizer that turns them into binaries. And then GHC can eat the binary while it's compiling the package. And then it will more or less, well, yeah, it was basically give us the compilation that we desire. And in this process, we can at any time just look at the JSON files and see the names in there as sanity checking. So some results. The hot call chains. Hot call chains with the inline pragmas. If we take the mean speedup of all 17 of our packages, we get a 4% mean speedup. If we use hot call chains with inlineable pragmas, we get a 7% mean speedup. So you'll notice that on each one of these packages, they'll get possibly a much better result on one type of pragma or another. And I think that goes back to the difference between the 2 pragmas. Like the inlineable pragma is generally going to be the safer option, but it's not very strong. And the inline pragma is much stronger, but it might also push through something that is going to cause like a big performance drop. Okay, so if we take the better case of inlineable or inline for each of those packages, and then we average together all of those better cases, we can see a 9% performance improvement. Okay, so an interesting thing that we noticed is with the system that we had set up, basically it will add the hot call chain pragma during desugaring. And during desugaring, the developer pragma has already been added. So we can't actually add our pragma if the developer pragma has already been added, which means that the developer pragma basically gets priority, and then it overrides whatever's in the hot call chain. So often, well, presumably often enough, the developers have a better idea of whether something should get an inline or an inlineable pragma, which is why whenever we add our method to their pragmas, we see a better result, basically. So if we look at just the developer pragmas on their own, the developers, they managed to get a 4% mean speedup across all the packages. If we add hot call chains with inlineable, and the developer pragmas, we get an 8% mean speedup. If we add hot call chain with inline on top of the developer pragmas, we get a 9% mean speedup. And if we take the better of the 2 of our approaches and we do the mean speedup of all of those, we get our 10% mean speedup. So a cool thing to note here is that, on the right, we have this little cluster of packages that have a nice big speedup. And on the left, the other ones are just virtually unaffected. There's no big slowdown to speak of. And we can also see that that holds for code size. So this is for hot call chains inlineable. There are only 2 packages that have between 6 and 7% increase in code size. The rest of them, it's less than 1%. So even if we run our thing on them, they're just not affected. And overall, the mean code size increase with this method was about 1%. Okay, so the conclusion of all this is a simple analysis. It's relatively inexpensive. It's conceptually easy to understand. It produces a significant speed up, which is safe because we're just using pragmas, and GHC knows how to deal with pragmas. And it works where machine learning has failed. And this helps a longstanding challenge in the Haskell community. So that's what I've got. Thank you. Any questions?
Yes.
So when you put an inline attribute or a pragma on a function, like every single time that function is referenced in the code, it would get inlined?
So if you attach a pragma to it, I believe so, yes. It's supposed to be inlined every time. So it changes at each time that it's inlined. So I'm not exactly sure if there are a few times in which it changes and then it no longer has that attached. But for the most part, yes. Okay,
because I guess I could imagine that like inlining the function in places where you aren't in the hot call chain, and so slow down like the binary on net. So I'm wondering if you could try the same thing, but like targeting call sites as opposed to definitions of functions.
Oh yeah. Yeah, no, this is definitely at the function definition site. It would be better if it was at the call site. But this was ever so slightly easier, and I got a publication out of it,
Fair enough.
Great. So does the inlining pragma also specialize recursive functions like fold or map? Or?
I think it will specialize if that information is available at compile time, but I think you can add an additional specialized information pragma or something like that if you know something that it doesn't know.
Because that's usually that's giving you a lot, so that might be something that you can extend it with.
Yeah.
I was a little bit surprised by your decision to focus on packages that already use the inlining pragma. Because I wonder whether it perhaps introduces a bias that perhaps goes against your own favor here. Because I may be naively thinking I could consider that these packages are already written by programmers that have very much perhaps knowledge of how GHC works and have performance on top of their mind. And perhaps you can achieve greater results, greater impact on other packages.
So the interesting thing is that you would think that the pragmas would make a big difference, but in practice they don't. We actually checked, and on most of the packages there's no difference. Sometimes there's even a detrimental difference. I don't know if it's with these packages specifically, but in general that's the case. We only had like a few packages that had a big difference.
All right. Any other questions?
Thank you for the great talk. It was refreshing to hear about the failed attempts because sometimes we can learn more from those. So I'm wondering about how independent are inlining decisions, because I could imagine if there's a method A, it calls B, B calls C, the inlining decision of B and C are not independent. But it seems that you're looking at values. What is the improvement of that decision? But are they independent?
I'm so glad you asked that question. This is going to be part of my thesis, actually. Inlining decisions, they're not independent. They're not at all. This is one of the things that we tried with collecting training data. We thought, we'll just attach a pragma to something and see if it causes a speed up. No, that will be affected by how many pragmas are on other things as well.
I think you mentioned that the profiler tells you which functions are responsible for a lot of the time, but also a lot of the allocations. And so I'm wondering if you saw a difference between pragmas that were supposed to fix functions that allocated a lot versus functions that just spent a lot of time doing computation.
I didn't look at that. Sounds cool though.
All right. Any other questions? So I have a general question about profile-guided optimizations. They're always like the promised land, right? We can achieve a lot with profile-guided optimizations, but it turns out that in practice, people usually don't use them, just because it's a bit annoying to get the profiles and everything. So do you think there's a future for them in Haskell? And are people already using this kind of optimizations?
That's funny. So I contacted someone who maintained one of the packages where we saw a massive performance improvement and asked him, how did you decide where to put the pragmas? And he said, trial and error. So I think people are kind of de facto using profile-guided optimizations manually. It'd be cool if we could automate that for the people who actually care.
So do you see a way of integrating that into the official GHC? And,
you know, if somebody wants to hire me and pay me to do that, that'd be awesome. Okay. I don't know. I hope so. I hope that this helps somebody somewhere.
Yeah, sounds promising. Okay. Thanks again.